Morning everyone, welcome back to the class. As in the last class we were learning, you remember that we were learning about energy. We have seen what is energy and how we are relating it with work done. Also we have seen there are many types of energy, as I've told you, and we are going to learn also. Especially we were seeing mechanical energy, and if you remember, mechanical energy is the sum of potential energy and kinetic energy. And then we were seeing the definition of potential energy, as we have seen that potential means that the energy which, because of the position of the body, potential energy is possessed by a body because of the position of the body or because of the configuration of the body. And depending upon this two condition given, we have seen that the potential energy is categorized or can be categorized under two categories. That is, it is of two types: gravitational potential energy and elastic potential energy. Gravitational potential energy, as it includes the word gravitation, we have seen it is related to the gravity. When the body is going up, we are changing the height of the body, or the body is coming down, then we are doing some work done, and that work done is going to store in the body as a form of energy specially, and that energy will be known as potential energy. Specifically, it will be known as gravitational potential energy. This we already have discussed in the last class. Also we have seen the expression, the mathematical expression for gravitational potential energy, which is U, which we denote gravitational potential energy by U. It is equals to mgh. Now we are gonna see the second type of potential energy, that is elastic potential energy. Okay, so before we start the elastic potential energy, let us see the word elastic. Where did you hear the word elastic, or have you heard this word before? Let's see. We are talking about elastic potential energy. Okay, so first we are gonna see what is elastic. This word actually you have heard before in class 9th, where we were learning sound. If you don't remember, let's see. Elastic, see, this is elastic, or the elasticity is a property of a body by virtue of which a body regain its original position or original shape and size. If not, it's not clear, let's see an example. If you take a spring and you stretch that spring, okay, now when you're stretching, let me say that this is spring, and if I am stretching that spring, that means I am applying a force, and that the shape of the spring will get deformed. Now what we will see, as soon as we remove the force applied on that spring, what will happen? The spring will regain its original position. Same thing will happen. You see, if you take a rubber, you stretch a rubber and you remove that force, what will you see? That the rubber will regain its original shape. So the property of rubber, or property of that spring, or property of any body, when we remove the force and it regain its original position, shape or size, that property of the body is known as elasticity, and such bodies are called elastic bodies. Is it clear? If I write like elastic, like if you take spring, whether you stretch the spring or whether you compress the spring, when you remove the force, if body regain its original position, then such type of bodies are called elastic bodies, and the property which the body possesses, that is known as elasticity. Not every body is elastic, as we know. If you take clay, you apply force. When we apply force, the shape of clay will get deformed, we know. And when you remove the force, will the clay regain its original position? No. That means the clay has no tendency or no property to regain its original position or original shape. That means the clay is not elastic, and the bodies which they don't have any this kind of property, they are not elastic, but they are called plastic. This is the next topic which we learn. We are here focusing on elastic. Okay, So all those bodies, like if you take rubber, of course rubber is elastic. When you remove the force, it will regain its original position. Like if you talk about a balloon, when you remove the force, it will a filled balloon. When you remove the force, it will regain its original position. So that's how we call it elastic. Okay, now let us see, elastic we have seen. Now let us see what is elastic potential energy. As we have learned, when we are talking about energy, how are we going to calculate energy? We are going to calculate the amount of work done, because already we have learned the amount of work done will store in a body as a form of energy. If it is stored in a body because of the gravitation, it will be known as gravitational potential energy. Here we are going to see what amount of work done is going to store, or how the amount of work done is going to store. See, if I take the spring, any spring, whether I am compressing the spring or whether I am stretching the spring, am I doing some work done? Yes, because I am applying some force, there will be some displacement, so I am doing some amount of work done, and that work done is gonna store in the body in the form of energy. Which energy? Elastic potential energy. Why elastic potential energy? Because when I am stretching the spring or compressing the spring, there is a change in configuration. We have learned that configuration means there is a change in shape and size. When you are compressing it, there is a change in shape and size. When you are stretching it, there is a change in shape and size. And whenever there is a change in shape and size, there will be a potential energy, specifically elastic potential energy, because elastic potential energy is stored in a body, or there is elastic potential energy in a body when there is change in configuration. Configuration means change in shape and size. And if there is a change in position, like if a body is placed here and I am changing the position of the body, then there will be change in, or there will be the concept of gravitational potential energy. That you can see, as we have seen that gravitational potential energy, the expression has mgh. M means mass of the body, g is acceleration due to gravity, and h is height. Whenever there is change in height, that means there will be change in gravitational potential energy. So we have seen that the potential energy is of two types. Gravitational potential energy, because of the position of the body. If there is change in position of the body, then there will be change in the gravitational potential energy. Also we have seen another type of potential energy is elastic potential energy. If there is change in configuration, that is change in shape and size, then there will be change in elastic potential energy. Okay, so this is what about elastic potential energy and gravitational potential energy. One more thing which I want you all to know is gravitational potential energy is depending upon mgh, that is mass of the body, which we know is constant. If you are talking about no change in mass, that means mass is going to be constant. G is the acceleration due to gravity, and h is the height. Okay, like if I am talking about the surface of earth, let's say it is the surface of earth and any object is placed here. Okay, now if I am taking, now just now from the surface of earth, what is the height? Height is 0. So what will be the amount of potential energy? It will be 0. Now let us say I am taking the object to a height h1. Okay, I am taking the object here. Let's say the height of the object is h1 here. That means how high it is from the surface of earth. It is at the height of h1. And let's say the mass of the body is m. So can you all tell me what will be the gravitational potential energy? That is mgh. What is the mass of the body? M. Acceleration due to gravity, g. And h. H is the height. What is the position now of the object? h1. So it will be h1. Is it clear to you all? Now let me change the height of the object again. Now I am taking the object to the other height. Let's say now the height of the object is h2. Is it okay? Like now the height of the object is h2. So mass is not going to change, it is m. Now can you all tell me what is the potential energy now? Let's say we are denoting it U2. Now m, because mass is going to be same, g is going to be same, and what is the height now? h2. Is it clear? Okay. Now from here to here and to here, what can you tell me, like whether u1 will be greater or u2 will be greater? Because here in both the expression m is same, g and g is same. Now only change is in the height, h1 and h2. Clearly h2 is greater than h1. So which one is greater? u2 will be greater than u1. Now if I ask you what is the difference or what is the change in the potential energy, of course it should be u2 minus u1, because this one is more and this one is less. So what will be the total or change? That will be mg. What is u2? mgh2 minus mgh1. You can take mg common here. So mg common, what is there? h2 minus h1. Is it clear, everyone? So that's what you can write u2 minus u1. And also we have learned, when we talk about u2 minus u1 or change in anything, we can denote it as delta u. Is it clear? So this is what is the expression of the change in potential energy. Also if you see like when we are talking about the gravitational potential energy, it basically depends upon the height, h, m, g, h. So we are talking about changing, and here you can you can talk about the reference point. Like if I am calculating h from the surface of earth, so then there will be a different, like this, let us say this is the surface of earth, a body is placed here. What is the potential energy? Since it is exactly on the surface of earth, no height, that means there will be no gravitational potential energy. But as I am increasing the height, h is increasing, so there will be a gravitational potential energy. Now if I ask you, if I place this object to the moon, if I take, so from the surface of earth, the distance of moon is very much, so the gravitational potential energy will be very much. Now if I change the reference point, like if I am measuring the height from the surface of moon only, I take this object, I put it on moon. Now this is the surface of moon. And now if I ask you, what is the gravitational potential energy of the body with respect to the surface of moon? So here is the surface of moon, here is the object, so there will be no gravitational potential energy. But if I ask you, what is the gravitational potential energy with respect to the surface of earth? Now surface of earth, from the surface of earth to here, there is a height or there is a distance, so there will be some gravitational potential energy. All I want to say is gravitational potential energy depends upon the position, also the reference point from where we are calculating the height. Is it? I hope it is clear now. So potential energy is of two types, elastic potential energy and gravitational potential energy. We are going to start with kinetic energy. We are going to see that when a body will possess kinetic energy. Before we start, let us see the meaning of this word kinetic. I think you know that what is the meaning of kinetic. Kinetic means something which is in motion. Then we use the word kinetic. So that means, as the word is very clear, that kinetic means that something which is motion, which means that when a body is in motion, the energy possessed by the body is or will be kinetic energy. It's simple, that something when it in motion, that means if a body is moving, what type of energy the body will possess? Kinetic energy. Is, I think it is clear with the name. Okay, now, and we are looking to calculate the expression for kinetic energy. And also we have seen, whenever we want to calculate energy, it is always easy to calculate the work done, because work done is the form of energy. So now if you see the definition first, so let's see the definition of kinetic energy. The energy possessed by a body when it is in motion, that energy is known as kinetic energy. Now we are going to see the expression for kinetic energy. So simple, we are going to calculate the work done. Now see the idea, how are we going to calculate kinetic energy? We are going to calculate the work done. The work done will be equal to the kinetic energy. If I tell you that how are we gonna calculate the work done, let's take a body of mass m. Okay, and now since it is a kinetic energy, the body should be in motion. So let's say the body is moving with the velocity v. You can take the velocity u, you can take the velocity v, it's just a matter of representation. Okay, so let's say the body is of mass m and it is moving with the velocity v. Okay, now when the body is moving, it is in the state of motion and the energy possessed by the body will be kinetic energy. Okay, now if the body is moving and we are applying a force to stop it, that means after a certain interval of time the body will come to rest, isn't it? Because we are applying a force to stop it. Before, now listen carefully, before coming to rest the body is doing some amount of work done. Yes, because it is moving with a force and it is having a displacement, so force into displacement, there must be some work done. That work done in the body, or that work done of the body will be stored in the body in the form of kinetic energy, and that work done we are going to calculate. Now please see, the body is of mass m moving with the velocity v, so it will be doing some work done. Before coming to rest, like if you apply a resisting force, it will come to rest, there will be no work done. So before coming to rest, what amount of work done is done by the body, that will be stored in the body, or that will be there in the body as a form of kinetic energy, and we wish to calculate that work done. Now if the idea is clear, let's see how are we going to calculate the work done. Okay, okay, now again we are going to see the same thing, that let's say a body is of mass m is moving with the velocity v. Okay, and when it is moving we are applying a force and eventually the body is coming to rest. So the final velocity of the body is becoming 0, still the mass is same. Is it clear? Now when the body is moving, we are considering that it is moving under a constant acceleration, or the acceleration of the body is uniform acceleration. The acceleration of the body is a. Okay, and when the body is moving, before coming to rest, let's say the body is covering our displacement or distance of s. Okay, this is the displacement of the body, this is the acceleration, this is the initial velocity you can say, or the velocity with which the body is moving, and this is the velocity when the body is coming to rest, the velocity is becoming 0. Okay, this is the displacement of the body. Now what are we wishing for? We are wishing to calculate the work done. Now let's go back. Now here you need to see that why are we calculating work done, because work done is going to store in the body as a form of energy. Which energy? Kinetic energy. So if we see the definition of work done, that will be force into displacement. This so we already have seen. So we have to see the force, we have to calculate the force, and also we have to calculate the displacement. Okay, now here if you see that force, as we have learned in the previous class, that force is equals to mass. According to Newton's second law, we have driven a expression for force, mathematical expression for force, that is F is equals to ma. If I write it somewhere, F is equals to m into a, mass into acceleration. This we have seen, so I'm going to use it here. The mass of the body is m, acceleration of the body is a, so the force will be m into a, isn't it? Into the displacement of the body which we are taking is s. Is it okay everyone? So that's how we have taken. Now we are going to calculate, m is given, a acceleration of the body is given, we are going to calculate this s, the displacement, how much displacement will be there in the body before coming to rest. So our idea is now going to calculate this displacement. Okay, so to calculate the displacement, we are going to use the equation of motion. We have learned the equation of motion in class 9, 3 equations of motion, that is v is equals to u plus at, the second one is s is equals to ut plus half at square, and the third one is v square is equals to u square plus 2as. Here we are going to calculate this displacement, and for that we are going to use the third equation of motion, which is v square is equals to u square plus 2as. Is it clear, everyone? Let me remind you what is here. This is the final velocity, this is the initial velocity, this is acceleration, and this is displacement. Okay, and if you remember, whenever there is a, since the body is eventually coming to rest as we are applying the resisting force, that means there will be acceleration in the body or retardation. Initial velocity is v, velocity is decreasing, and now eventually coming to 0. That means the velocity is reducing, and when the velocity is reducing, there will be retardation in the body. And when there is retardation in the body, we use minus sign instead of plus, if you remember. So instead of using this plus sign, I am going to use minus, since there is a retardation in the body. I hope it is clear. Now let me put the values according to the given condition. Final velocity. What is the final velocity of the body? It is coming to rest. That means the final velocity is now becoming 0. Initial velocity, which we are denoting by v, so simply we can write v square minus 2. Acceleration is given, uniform acceleration is given a, and this displacement we don't know, which we are looking to calculate. Now if you see, this 2as quantity is with minus sign, can we bring it to the other side? And when we are bringing it to the other side, it will become plus. So it will be 2as is equals to v square. Is it clear? This minus 2as will come here. It will be 2as is equals to v square. We have to calculate s. So we are going to leave s here, and we will take this 2a to the other side. So s is equals to v square upon, since it is in multiplication, it will go to that side and it will come here in division. So the displacement is now coming v square upon 2a. We have calculated the value of displacement in terms of velocity and acceleration. Now we are going to use this value of displacement and going to put it there in the expression of work done. Okay, so now let's see if you can recall that expression. I'm going to rub it because I am not having the space here. Now if you can go back and you see that work done which we have written was force into displacement. Force we have written as m into a, displacement we were actually denoting by s, and just now we have calculated the expression for s, that is coming v square upon 2a. Isn't it? We have kept the value of s here. Okay, now if you see a and a, we can cancel a and a, so the expression, final expression is coming 1 upon 2. So if I write the numeral here, m into v square. So this is the work done by the body before coming to rest, which is w half mv square. And as we have seen the definition, the work done by the body before coming to rest will be stored in a body as, or in the form of kinetic, or it will be the kinetic energy of the body. So simply, what is the expression for kinetic energy? That will be half mv square, which we are aware of. It depends on two things, that is mass and velocity, and also the kinetic energy will be there in the body because of its state of motion. Okay, we are going to see the forms of kinetic energy. There are three forms of kinetic energy. As we have seen that kinetic energy is possessed by a body which is in the state of motion, and there are three forms of kinetic energy. First one is translational kinetic energy, then we have rotational kinetic energy, and then we have vibrational kinetic energy. Now let's see one by one. Translational or translational motion. Translation, when a body is moving in a straight line. Translational motion, linear motion, or motion in a straight line. Like if a car is moving, a train is moving, a bike is moving in a straight line, so then there is a motion in the body in one direction. So that motion will be translational motion. That motion, there is a change in position in one direction. So that's how we call that motion as a translational motion. And since the body is in motion, so which type of energy it will possess? Kinetic energy. So overall we call it translational kinetic energy. You can take many examples as I've given you, that a body, like a motion of train, a motion of bike, car, whatever, any object moving in one direction. Okay. Next we have rotational. I hope you all are getting it now. Rotational means something which is rotating about an axis, or like if a fan is rotating or we are rotating about an axis or about a point, that will be a rotational motion. A wheel, we are talking about a wheel or something like that. You can talk about electrons. They are also moving. Rotational motion they have. They are moving around the nucleus. So all these type of motions are known as rotational motion. And since the object are in motion, so there will be a type of energy which will be kinetic energy. But especially which type of energy? Rotational kinetic energy. So you can give the example of fan, you can give the example of planets, rotational motion of the earth, rotational motion of the earth, electrons, whatever things are rotating, that will have rotational motion. And which energy? Rotational kinetic energy. Vibrational, as we know that the atoms or any body which are vibrating or having a to and fro motion, that means they are vibrating. If they are vibrating, that means they are in motion. If they are in motion, which type of energy they will possess? Kinetic energy. And specifically which type of energy? Vibrational kinetic energy. Is this okay? So we have translational kinetic energy, moving in one direction. We have rotational kinetic energy, if the body is rotating. If the body is vibrating, which energy the body will have? Vibrational kinetic energy. For a body, or there can be a body which can possess two types of energy at the same time, or all three types of energy at the same time. If you are talking about a monoatomic gas, okay, monoatomic gas, that means if we talk about helium is monoatomic. If we talk about argon, it is monoatomic. So if you talk about a monoatomic gas, so there will be only one particle and there will be only one type of motion, that is translational motion. But if we talk about the diatomic or polyatomic, like if you talk about NO2, or if you talk about H2, these type of gases will possess rotational kinetic energy as well as translational, because there will be two atoms, so there will be rotation also and there will be translational motion also. So they will possess translational kinetic energy as well as rotational kinetic energy. So these are all the form of kinetic energy. Next we are going to see the work energy theorem in the next class.